Okay, good afternoon. There's one empty seat, it looks like. Oh, it's already claimed. No, there's no empty seat. I see. Okay. Terrific. Well, good afternoon. Thanks for coming. If you don't fit in the room, there is a webcast, as I understand it, and so you'll be able to, and also all the slides will be ultimately posted online so that you can come and see them. But I'm very happy to have the opportunity to be here with you to talk today about aspects of the carbon cycle. As you know, we really do think of our national laboratory as having at the core of its mission to seek to work on the most important issues of the day for the nation and for all of humanity. And for some time now, the laboratory has been organizing itself to address the issues that relate to the carbon cycle and the imbalance in the carbon cycle which has occurred as a result of human activity. An issue of very deep interest to all of us, and one which crosses many, many boundaries of science and really challenges the laboratory and the science community broadly to come up with new and innovative solutions. So today I'll be talking to you about that and trying at the same time to show to you the extent to which it also leads to a very positive vision for what our future can look like. Of course, the origin of the discussion does relate to the fact that anthropogenic emissions of CO2 are about 100 times the natural flux that would occur geologically with respect to carbon. So that today we have a situation where the combustion of fossil fuel corresponding to 8 or so gigatons of carbon puts CO2 into the atmosphere. Some of it returns to land or to ocean in terms of being taken up by the biosphere or dissolved in the ocean, but a great deal of it ends up in the atmosphere itself. And so it's important for us to understand the implications of that and how it all works. And it's important for all of us who work at the laboratory, whether we're scientists in disciplines that relate to this or ones that do not, or if we're people who are here supporting the laboratory in its mission, it's important for all of us to know something, at least, about the basic science that underlies this whole topic. And that's why I wanted to speak to you today. And so this is intended to be, in some sense, tutorial and to be helpful to you as you seek to educate yourself about it. I've spent the last couple of years myself reading many different sources and trying to bring myself up to speed because it's not the area of research that I grew up in myself. And you'll see, in many cases, available on the slides and in those that will be posted, materials where you can go and read more. So the beginning of our discussion today concerns this observation, which shows the concentration of carbon dioxide in the atmosphere as a function of the year, going here from 1,000 to 2,000. And what you can see is it's holding very steady, and then at a certain point in time, it starts to take off. And if you look carefully at the break point at which you start to see it taking off, it's right around this year of 1769, which also coincidentally happens to be the time when there was a breakthrough in the design of the steam engine. So the question is, first of all, is this all correct? And secondly, what are all of its implications? So we're going to go through this step by step, and we're going to look at a lot of the history of how this developed, this area of science. And we're going to try to answer the three questions here. Does an increase in atmospheric CO2 influence the Earth's temperature? Is CO2 increasing? And is that increase due to human activity? So what is the evidence for that? And then we'll ponder this question, to which there's no definitive answer. Can't we simply adapt to any changes that might arise from the increase in CO2? We don't for sure know the answer to that. So I'll be sharing with you some of the things that we do know and some of the things that we don't. So as I mentioned to you, we're going to start with some history. And this is a fantastic problem to look at if you're interested in the history of science, because it has developed, this whole discussion around this topic has developed during the period when foundational subjects of modern science also developed, namely thermodynamics, statistical mechanics, quantum mechanics, spectroscopy. some of the very fundamental areas of science developed even as this question was being raised. And so our appreciation and our understanding of this subject has really become much deeper as the fields of science have matured. And so we will go through the 19th century classics first, and there are three that we can call out most clearly due to Fourier, who you will be familiar with from his mathematics of Fourier transforms if you've studied science, and through John Tyndall, and through Svante Arrhenius. So we'll go through these three very classic moments in the history of the development of this subject first. So starting with Fourier, in the time of Fourier, there was a great interest in understanding how heat flows between different bodies. That was a key piece. You'll remember the steam engine had just been discovered developed some decades before, and the whole basis of that was the science of thermodynamics, how heat flows from one substance to another, from hot to cold, and how different forms of energy can interconvert into each other was an extremely rich subject of science. And Fourier, who was developing some of the mathematical methods of transforms and others that you are aware of, was developing those methods specifically to try to analyze problems related to the transfer of heat. And in the course of his deliberations, he considered the issue of the temperature of the Earth. And you can see why it's an intriguing problem, because you've got the sun, which is extremely hot, and it's sending out light, which comes and hits the Earth, and it warms the Earth. But the Earth is, of course, embedded in an interplanetary medium that's extremely cold, so the Earth can, in turn, once it's warmed up, radiate heat outwards into space, which is very cold. So there's a very hot body embedded in a cold one, and you can imagine the effort to try to calculate what is the temperature of the Earth, because it's being heated on the one hand and cooled on the other, and the balance between those two can lead to a balanced temperature. And so you can see here in his language, the surface of the Earth is located between one solid mass, whose central heat may surpass that of incandescent matter, and an immense region whose temperature is below the freezing point of Mercury. He applied all of his tools to the best of his ability and calculated a temperature that was some 30 degrees too low. So according to the calculation done to the best of his ability of the energy coming in and the energy going out, in the end, the temperature came out very, very cold. And so considering this, he was the first person ultimately to recognize this very interesting aspect of the problem, namely the role that is played by the atmosphere in determining the net temperature of the Earth. And he says, the heat of the sun arriving in the form of visible light has the ability to penetrate the transparent solid or liquid substances. In this case, the visible light can penetrate the atmosphere, but loses this ability almost completely when it is converted by its interaction with the terrestrial body into dark radiant heat, by which we would mean infrared light. So what happens is visible light comes in and hits the planet, warming it, and then the planet emits infrared light, and the infrared light itself is no longer transmitted by the atmosphere, but some of it is in fact reflected backwards, so some of the heat is retained, and if you like, the ability of the planet to cool itself is retarded a little bit, and that means that it's being warmed at a certain rate, but cooled a little bit less than what the calculation originally showed, and that would, of course, result in a net increase in the temperature and could restore the temperature approximately correctly. In other words, correct calculation of the temperature of the Earth requires taking into account the role of the atmosphere and the greenhouse effect. So that was 1824 and 1827. Now, up to that point, the mechanism by which that could actually arise could not have been understood. But subsequently, people started to understand more and more about the very, very early stages of the interaction of radiation with matter. And Tyndall was studying the effect of infrared light on the transmission of infrared light through various gases. He had tubes of gases and was creating infrared light and trying to see what got through and what did not. And what he found was that infrared light was strongly absorbed by gases like water and CO2. And it turns out that that, of course, provides an understanding of the physical basis for the influence of water and CO2 upon the temperature of the Earth. In other words, visible light comes in, heats the planet. Infrared light is emitted by the planet, and that infrared light is absorbed by the gases of CO2 and water. Here you can just see little cartoons which show the vibrational motions of CO2, which are ultimately induced by the infrared light. So when the infrared light passes through the gases, it creates motion in them, absorbing that light and attenuating it. And in many cases then reflecting it back down towards the planet, and some of it back up again, but some of it back down, and that ends up producing a net warming. And in this rather colorful 19th century language, he says, as a dam built across a river causes a local deepening of the stream, so our atmosphere, thrown as a barrier across the terrestrial rays, that's the infrared terrestrial rays, so the atmosphere is thrown as a barrier across that, produces a local heightening of the temperature at the Earth's surface. And this other quote of his, without water, the Earth's surface would be held fast in the iron grip of frost. So today, today we know that that is true not just for water, but in fact, actually, as I'll show you in a little bit, we know that if CO2, for example, were completely removed from the atmosphere, we would have a very cold planet indeed. The next really important step, and in many senses, I would say perhaps the definitively important paper in this whole literature is the 1896 paper by Svante Arrhenius. Arrhenius was a Nobel laureate in Sweden who, many of you who have studied chemistry will be familiar with his name from the Arrhenius law. He studied ultimately the processes that lead to activation. How much energy do you have to input in order for a chemical reaction to occur? And Arrhenius had a friend who was very, very interested in the ice ages. So he was in the academy, the Swedish academy, and one of his cohorts there was trying to explain what led ultimately to the ice ages occurring. So at that time, of course, it was known that the temperature of the Earth was partly controlled by water and CO2, and so they began to think about how those things could actually influence the temperature. And so Arrhenius wrote this paper in 1896 called On the Influence of Carbonic Acid, that's CO2, in the air upon the temperature of the ground. And in this 1896 paper, he performed the first calculation of what we would call the climate sensitivity. In other words, he imagined taking the CO2 concentration, which they very laboriously obtained by studies of how moonlight is transmitted through the atmosphere and other such things. It wasn't easy to know the concentration of CO2 in the atmosphere at the time, but he got a pretty good number on it, and then ultimately tried to calculate what the temperature change would be if you made CO2 half. Remember, he was interested in the ice ages, so first he calculated whatever, he made CO2 half, and of course found the influence that it would decrease the temperature quite a bit, and that in fact that could have been one of the reasons for the ice ages. But then, of course, as long as he was at it, and towards the end of the paper, goes through the calculation and discusses, well, we can see all of these factories, and we know that they're emitting CO2. What would happen if you doubled it? And so he calculates that a doubling, and in his first calculation in 1896, he showed that the temperature would go up by about 5 degrees Celsius, which turns out perhaps to be a bit of an overestimate in the way that he calculated it. Subsequently, he refined his calculation, including so-called feedbacks, which we'll be coming back to momentarily, and he got a number of around 2.1 degrees C, which is an awfully good number, although not necessarily for all the right reasons, but an awfully good number. Interestingly, also, he comments in the paper that don't worry too much about this doubling of the CO2. It would take a very, very long time, perhaps 1,000 years, before there could possibly be enough anthropogenic CO2, because he calculated how many factories there are, how many people there are. Not going to be a problem. Now, those ideas laid out many, many of the basics, but in the early 20th century and throughout now into the period to today, a lot of physics and a lot of chemistry was discovered and understood about spectroscopy, how radiation interacts with matter, and other such things, and that informs our thinking today. So here you can see the black body spectrum of the sun, And that's coming in. It's a very hot. The sun is a very hot body, so the photons that come out are higher in energy. The Earth is a rather colder body, but it can lose energy by emitting light. And remember, the basic way to understand this, if you have a molecule that's excited and it's vibrating like those cartoons that you saw, if it emits a photon, it can lose some energy. So Earth can cool itself by emitting that light. And so the Earth will emit light that's in the infrared region because it's a much colder body than the sun is. And so, this disparity between the regions of the spectrum reflect the differences in the temperature of the two bodies, the sun and the Earth. And the light that's emitted by the Earth has to pass through an atmosphere which has in it a variety of gases, water vapor, carbon dioxide, oxygen, methane, nitrous oxide. There's some Rayleigh scattering, which means just scattering off of density fluctuations in the atmosphere. So many different things can go on. And you can see here the importance of the two most significant gases, water vapor and carbon dioxide. And there are many, many things to note here. When Arrhenius first published his paper, shortly later, another colleague of his objected and said, well, the CO2 is going to be saturated because if you measure the path length, how much CO2 I have to have before all the light just gets stopped, it's not all that much. And therefore, I think that in the end, doubling or halving CO2 won't make that big of a difference. We know that not to be true for at least two different reasons, which I'll be explaining to you. One you can see right here. This shows one of those absorption lines. It's due to that kind of bending motion of the CO2. And what can happen, of course, which is something that's only understood when we think about both the quantum mechanics and the statistical mechanics, is that the carbon dioxide, the wings of the spectrum, can broaden out. It's not just the center line of the peak. In other words, as you put in more CO2, the line gets broader and broader the lines you can populate and absorb at the edges. And you can also see that it looks like CO2 is kind of placed in regions that are like windows in the spectrum of the water. So you can imagine that there can be a lot of water there, but addition or subtraction of CO2 can in fact make a lot of difference in how light comes in and out of the planet in the infrared regime. In fact, fortuitously for us, there's a very nice article in this month's Physics Today which goes through much of the physics that I'm describing here as well, although not quite as much of the history. And it allows you to think about how you would go about calculating this. Much of this was really enumerated in the 1920s and then maybe a little bit into the 1950s, by which point this was really a fully settled topic in many ways. So what you can see here is just the idea that what happens is that deals with this issue of the penetration length. What you can see is an infrared photon can be emitted, and then we can imagine the atmosphere as consisting of a series of layers, each at a different temperature. So some infrared light can be emitted and then reabsorbed, and when it's then emitted again, it could go up or down, and of course then it can get absorbed and re-emitted. And so you can imagine the light trying to escape, and it just can't get out because it keeps getting reabsorbed until it gets to that very, very, very uppermost layer, at which there's not much CO2 anymore above it, and then it does escape. And at that height, of course, when it finally does escape, when that photon does escape and leaves the planet, okay, then there is a cooling taking place at that point, right? Because as you remember, when the light leaves, it leaves the molecule in a lower energy state. That's a cooling, okay? Now, as you imagine that happening at different altitudes, what you can see here is that as you go up higher and higher in the atmosphere, the temperature, of course, drops. So what you can see is that as you go up to a higher altitude, if we put more CO2 in the atmosphere, the altitude at which the photons finally can escape goes higher and higher, and that occurs at a lower and lower temperature because the altitude is getting higher, and as you go up in the atmosphere, the temperature goes down. Well, of course, if the height at which the photon leaves finally is higher up and therefore colder, the effective cooling rate of the planet is decreased compared to if it's at a lower altitude. This is why, remember, the sun is coming in and heating, the escape of these photons is cooling, but if the cooling takes place from a lower temperature, the efficiency of the cooling is reduced. And this is why, even though you can saturate that line, it turns out that as you put more CO2 into the atmosphere, you do end up increasing the temperature of the Earth because the cooling rate is not as high as it had been before. That's why this thing isn't really effectively saturated. Up here you see simply the black body curve. This is the curve you would get if it was a simple body at a single temperature. And you can see this big divot here in the peak of the emission spectrum of the Earth in the infrared region, corresponding to the region of the CO2 absorption. And that is what relates ultimately to the inability of the Earth to cool itself as well as it would were the CO2 not there. You can also see the influence of the water. I mentioned to you that when Tyndall said that the planet would be in the iron grip of frost without water, that the same thing is actually probably true of CO2. Here you can see a recent calculation from the NASA GISS group showing in a computer now, not a real experiment, of course, thankfully, but an experiment in which all the CO2, they allow in a computer model the temperature of the Earth to completely equilibrate, and then since it's on the computer, they can just take out all the CO2 and then see what happens to the temperature as a function of the time. And what you see is a very quick drop in the temperature, well below the temperature where water condenses out and becomes all frozen. So we lead to what would be called a snowball Earth, which would happen if all the CO2 were removed. This is another aspect of understanding why CO2 is such an important control gas on the temperature of the Earth. And it has to do with the fact that water and CO2 are both very important greenhouse gases, but water can condense. In the relevant temperature regime we're working in, carbon dioxide really does not. So that's why the CO2 ends up playing this very critical role in controlling, ultimately, the atmosphere. Now, of course, today, we're not in much danger of CO2 abruptly being removed from the planet. We're in the opposite configuration, where we're putting CO2 in. But in answer to the question, from a strictly scientific point of view, true or false, does an increase in atmospheric CO2 influence the Earth's temperature? The answer is definitely yes, transcendently so. This question has been answered as definitively as it can be, and we know for sure the microscopic mechanism, and we can calculate the magnitudes very precisely, and really, in some sense, the ability to go through this in such a systematic way is, I think, really a triumph, ultimately, of the development of all those scientific disciplines that I've spoken to you about as we've gone along. The next question, is CO2 increasing? And is that increase due to human activity? So let's take a look and see. And remember now, what we're saying is that the CO2 ends up acting essentially like a layer inside a thermos, an extra layer inside there, so that when the warming of the sun comes in, it doesn't allow the heat to escape. If the CO2 is increasing, that means that we will have a little bit of warming going on. So let's look and see how that works. So first of all, here is the famous Keeling curve in which you can see the measurement of carbon dioxide as a function of time obtained originally at Mauna Loa in Hawaii. There's actually very interesting stories relating to this, which I'm going to skip them for now, and we'll just look carefully at these measurements. What you can see is this oscillation. The oscillation in CO2 as a function of the year takes place as the biosphere breathes. As life is influenced by the seasons, you get more biological uptake of CO2 to grow plants. So that's what makes this kind of annual oscillation that you see here. But superimposed on top of that, you can see this increase in the CO2 as a function of the time. And these measurements have obviously been going on for decades now. It started during the year the International Year of Geophysics, which was 1957, is when Keeling was able to first start doing these measurements at Mauna Loa, and has continued ever since. And they have been done very, very precisely, very, very careful measurements, done not just at this site, but now at many sites all around the world, which ultimately show an agreement, because it turns out that when you emit CO2 into the atmosphere, you share it with everybody in the world. It rapidly disperses around. So there's a global concentration that can be measured very carefully. And you can see that it's increasing here. It's starting just over 300 parts per million, and it's starting at 310 here, and going up now to around 390 parts per million, so that you can see the increases that are happening, and that, I think, is truly beyond dispute. Now, if what happens is that as the CO2 is emitted, if it comes, let's just hypothesize here from elementary chemistry that what happened is that the CO2 came from burning fuel. And so you can see here a fuel reacting with oxygen. Fuel plus oxygen will produce CO2 plus water. So let's just imagine hypothetically that it was true that this increase in CO2 came from combustion of hydrocarbons. If that were true, then we would expect that when we put more CO2 into the atmosphere, the amount of oxygen would also be going down. And so Roger Keeling, who was David Keeling's son, has dedicated himself now to measuring many different gases in the atmosphere, but among them, oxygen. And so here you can see the ratio of oxygen to nitrogen in the atmosphere as a function of the time. And you can see, again, this oscillation, but you can also see the decrease. Now, you don't need to be too worried about it in the sense that oxygen is starting out at about 20%, and the small changes in parts per million are not going to prevent us from breathing. But on the other hand, what you can see is that the basic stoichiometry of the reaction, so many molecules of hydrocarbon react with so many of oxygen to produce so many of CO2 and so on, ultimately, you can see that essentially reflected in the oxygen that is being consumed from the atmosphere as we are burning the hydrocarbon. So that is a very strong implication that the origin of the increase of the CO2 is from the burning of the fossil fuel. You can see it in the balance of the chemical reaction. It also turns out that there are isotopic signatures. It turns out that plants will bring in and fix CO2 and make biomass, and ultimately that biomass is what has created our fossil fuels eons later. But the ability of a plant to consume the CO2 happens at a slightly different rate for the different isotopes. The lighter isotope, carbon-12, is taken up by a plant more readily than the heavier carbon-13, and still more readily than the even heavier carbon-14. So if you look inside a plant, you will find that it has an enhanced amount of carbon-12 inside of it compared to carbon-13, and even more so compared to carbon-14. And it turns out that if you take fossil fuel, it's very old carbon, and you burn it, and you put it into the atmosphere, you increase the relative fraction of carbon-12 compared to carbon-13 in the atmosphere. And if you go and look inside the atmosphere, you can see that the fraction of carbon-13 in the atmosphere is slowly decreasing because we're putting into the air carbon that has come from the burning of fossil fuels, which is enhanced in carbon-12. So that you can see this isotopically as the amount of CO2 is increasing, the amount of carbon-12 relative fraction in the atmosphere is decreasing. Likewise, you can see that for the carbon-14. The issue with the carbon-14 data is that it ends in 1950 because carbon-14 was created from the atmospheric tests of nuclear weapons. So after that point in time, the data just can't really be used for the 14. Eventually, that will be restored. In fact, you can go back and look over 800,000 years, which is as shown here. This shows the amount of atmospheric CO2 over 800,000 years, principally obtained from looking at ice cores. And if you do that, you can see this oscillation in the amount of carbon dioxide in the atmosphere as a function of the time. And these, of course, you can readily imagine, these are the ice ages. The changes in these corresponded to the glaciations and deglaciations which occur with the ice ages. And these are the things that Arrhenius was trying to calculate, and the fractional changes that he was putting in the amount of CO2. You can see they're not so unreasonable. If you were, say, at 280 and you went down to 140, it's about a factor of 2, and that's enough roughly to explain an ice age versus not an ice age. But here on top, you can see superimposed the data, which shows that during this period of 800,000 years, it has not been above about 290 or so. But in the period post then, which is the data that I started showing you earlier, it's come up now to just below 400 and is, of course, increasing every year. These are, of course, simply scenarios. We don't really know that this is exactly what's going to happen, but plausible scenarios for different degrees of emissions based on how much we are putting out these days put the numbers in this kind of a regime. So ultimately, we could be looking at being at 600 or 800 or someplace in there, parts per million, in the future. One thing which has scientists deeply concerned, if you go back just a moment here and look at this data, and you can see the glaciations and deglaciations, I should be careful here and just say, by the way, that it's not implicit in here that this is strictly caused by, that CO2 is leading to is the only factor leading to the temperature changes. It is thought and believed that actually the intervals of warming actually are precipitated by some changes in the tilt axis of the Earth, so-called Milankovitch cycles, which occur periodically. And that one of those starts, that initiates a little bit of warming of the planet. And as a follow-on to that, CO2 is released from the oceans. And that release of CO2 then helps drive this increase in the temperature. And then they get these kinds of up and down kind of swings. But what you can notice here is that fundamentally this looks kind of like a system that has certain characteristic timescales associated with it in which it's changing in one direction or the other, characteristically over certain time intervals. And one of the things that does concern people quite a bit is the abruptness. This would show the last emerging from an ice age, and you can see that it's going on over some tens of thousands of years versus, say, 100 years in which we're increasing the CO2 by amounts larger than it would typically change during a period between an ice age. And if you're familiar from thinking about the frequency responses of things, you can imagine we're putting the system into a different regime in terms of how we're driving it. And so it's a little bit hard to know what all the implications of that are or how the system will respond because of the abruptness of the time scale. In any case, I think that we can certainly agree that CO2 is absolutely increasing, that an increase in CO2 ultimately is expected just from the energy balance to lead to an increase in the Earth's temperature, and that in fact, yes, that increase is due to human activity, as evidenced by the isotopes and the balance of the chemical reaction and many other ways of looking at it. So the question becomes, can't we simply adapt to any changes that might arise? And the answer to that, as you will see, is one we're going to go into now. This shows here the global mean temperature record since 1880, obtained by the 3 different groups that have studied these data carefully, as shown in the IPCC. And you can kind of see this increase in this more recent time interval. I'm very gratified that Rich Muller is here and his colleague, Robert Rohde, who you may have noticed on some of the earlier graphs, I had showed some graphs that credited Robert Rohde because he's created a beautiful website with some of the best descriptions of much of the data here. But Robert and Rich are deeply engaged in a new project called the Berkeley Earth Surface Temperature Analysis Project, the BEST project. And one of their goals is to vastly expand the number of reporting stations that will be looked at for calculating the change in the temperature over time, up now to about 39,000, and to do that in an open source way where all the data is available openly and in where the very careful analysis statistically of the weightings of the relative stations, which if 2 stations are very close to each other, the amount of relatively new information is not the same as if they're far apart, and so on. There's a lot of statistical analysis that has to go in carefully to looking at that. This project, which many of our colleagues are engaged in, is to very open source way put all that data out there so that anybody that has any questions about it can go and look and see the raw data and see it for themselves and poke around and say, do I like how this was done or not? So it's all there. So far, they've only analyzed 2% of the 39,000 stations they have, but as you can see, it looks very much like the previous analyses that have been performed. Just in this case, it's done very, very systematically. Here's some of their data. They've obtained very beautifully graphically. These show individual temperature stations as a function of the time. And here you can see the average, the global mean temperature of the Earth bouncing around as a function of the year. We're stuck in the 1860s right now, and there are very few temperature reporting stations. And of course, as the globe would get warmer, we would head up to more red colors. Colder, it would be more blue. And So we can go through this. It takes quite a while, so I'm just going to speed it up myself. But let's just go up right here. For example, you can see more and more stations, particularly in the United States and Europe, a few elsewhere. And we can come right up here, and Rich pointed out to me that I could look carefully here if we just kind of tool our way along. And, oops, right here now, that's the dust bowl. You see that right there, the red over there? That's the, so you can see, the dust bowl phenomenon. And each one of those blue and red things where you see a big blob, there's something significant that happened during that period that people would like to understand, all different kinds of things. The next one to kind of look at here carefully is the year 1998, which is the hottest year on record, although perhaps this year will be similar, very close anyway. But here you can see, so that's 1998. Oops, we went by it there, didn't we? There's 1998, which was the hottest year on record. And then you can kind of finish it out. And you can see that over time, indeed, the temperature has increased maybe 0.7 degrees or so over that time interval. Okay, that's about how much it has increased. Now, this can be compared, of course, to computer models of different types, and you can put different levels of trust in those computer models. But here you can see the black data showing the mean temperature, similar to what was shown in those previous graphs. And the red kind of shows the average of all these different models, because lots of people make different models, and they're not all the same, and we'll go into that in a moment. But you can see, for example, important events like volcanoes. Volcanoes, of course, put a lot of ash into the air. When a lot of ash comes into the air, it screens some of the sunlight. Therefore, there's less warming, so there's a decrease in the temperature. All those things are in the models. They're not some giant surprise, and you can see them in there. And you can see this increase, which corresponds to maybe 0.6 or 0.7 degrees Celsius. Now, these are the models which include so-called all of the forcings. In other words, they include all of the greenhouse gases that are emitted and other things which happen due to people activities versus all the natural forcings like volcanoes or changes in the intensity of the sun or whatever else might go into calculating a possible forcing. Taking into account all of those to the best of our ability is shown here. This shows the same computer models, but on the computer, remember, you can add and subtract stuff as you like, so you can include only the natural forcings, in other words, volcanoes, any change in the intensity of the sun, all those kinds of things, but take out all of the human ones, and you can just look at the difference between those two, and the difference between those two corresponds to the temperature increase, which is happening because, as we know, if you put more CO2 into the atmosphere, the cooling rate is altered for the planet, and of necessity, by thermodynamics, that means the temperature of the Earth is going to have to slowly go up. Now, it won't all happen in one fell swoop. It won't happen in an hour. It will take a certain amount of time for that to catch up and to occur in its completeness, which it hasn't yet, but that's what's happening. So here are some constraints on us as we start to think about this problem. One of them is, how long will the effects of this be in place? Let's say we just stopped emitting CO2. And so here's an article by Archer, who works into this. Don DePaulo has educated me a great deal on this. And you can see here that if you just put a bunch of CO2 into the system and then watch it go away, it takes a very long time, because the natural way in which CO2 can be removed from the atmosphere, CO2 comes into the atmosphere in the natural cycle by volcanism. Volcano takes rocks and burns them up and puts CO2 into the atmosphere. It's ultimately returned by going into the oceans and land, and then by some kind of subduction, which then later on ends up making rocks. And it takes a long time for those rocks to form once you put the CO2 in there. So there's a very slow reaction that will eventually produce rocks. But the time scale for doing that is sort of tens of thousands of years. So this is a scenario where we emit 1,000 gigatons of CO2. Now, every year we emit today about 30 gigatons of CO2. So we might be able to do a scenario like this by emitting 30 gigatons for 30 years, roughly. But this would be if we actually burned up all the coal deposits. So it's 5,000 gigatons. And you can just see kind of two differences between these scenarios. So in this one, we emit a certain amount and then stop. In this one, we emit a certain amount and stop just because we can't find any more to emit. And and what you can see here is that in this case it sort of stabilizes at a little bit around 400 parts per million, which we're pretty close to right now, for an extended period. And in this one it goes up higher. 800 parts per million corresponds to what people calculate to be an ice-free Earth. So one constraint is that whatever you do, it takes a long time for these things to be reversed. That's the nature of the planet, unless, of course, we did something actively to remove it. It's another story. Now, the next question is, how much temperature change do we actually really expect? And this is where people will come from the public and say, we would like you to really tell us all the consequences, calculate them on, and be definitive, and just tell us the answer, please. And unfortunately, it's not quite so simple. Because, and you remember I mentioned to you that maybe Arrhenius didn't get absolutely everything right in his calculation. He said, I doubled CO2, and then he calculated out the numbers. And why is it so tricky? Well, in his case, he didn't have all of the statistical mechanics and quantum mechanics and spectroscopy that we know today. But even if you know all those things absolutely perfectly, it's still really not possible today. And it may not be possible anytime soon, probably not, actually, to really make a definitive statement on this. And that's because of all the so-called feedbacks. And just to remind you, what do we mean by a feedback? Well, an example of a feedback might be that when the planet gets a little bit warmer, more water evaporates from the ocean. Water is also a greenhouse gas. So the CO2 that you put in there warms the planet. Then that evaporates more water, which then in turn warms the planet a little bit more. That's a positive feedback, okay? There can be negative feedbacks as well. For example, you might get more clouds forming. And if there's more cloud, for example, if you're burning coal, you make a lot of aerosol particles, and the aerosol particles condense little droplets, and the little droplets somehow make more clouds. Then you can imagine those reflecting. It's a little bit like having an extra volcano in there. That's a cooling effect. That goes the opposite way. So there are feedbacks which can be positive, and there's feedbacks which can be negative. There's a bunch of different feedbacks. In fact, you can just sit there listing feedbacks and thinking of them, and there are more and more of them. And so that's a whole issue of how do you include all of those? How do you know you've got them quite right? And it turns out that if you look at the temperature change that we expect at the end, there's some delta T0 here. This is what we would calculate just based on no feedbacks. Just put the CO2 in and do the simple, or the balance of photons coming in and out, calculate the height at which the photons escape and all this kind of stuff. And you'd get some number. It's about 1.2 degrees C. But then it's got this 1 minus F. That's because the feedbacks are a correction. And it turns out that that correction might be in the neighborhood ultimately when everything, all the different feedbacks are added up of about 0.6, making this factor of about 0.4. So it's 1.2 divided by 0.4, which puts you in this sort of 2.5 to 3 degrees C kind of range, okay? And you say, okay, well, there must be some distribution of feedback factors, okay? I mean, I can't know what all of them are because there's a lot of them. So let's just imagine, for the sake of argument, that their distribution is Gaussian, okay, normal distribution. Just there's some range of them, okay? And I can't tell you if it's exactly 0.6 or 0.55, but there's some probability for each one of these. And then you say, okay, then I should be able to just calculate the temperature. But you'll see that it's 1 minus F, and this has this guy. That ends up making this 1 minus F factor. If F is 1, of course, then the change in temperature diverges. It's delta T0 divided by 0. That becomes a very large number. And that's what makes the so-called long or fat tail in this distribution. What that means is perfectly plausible scenarios can produce really big possible temperature changes. Or another way of saying this is we can work all we want to try to understand better and better and better the feedbacks, but we're never going to be at a point where we can say this is absolutely the value of the feedback. There's going to be some distribution in those in our knowledge, and we're not going to know, but there are going to be finite and significant probabilities that we might get up into the 6 or 8 degree range. And at that point, really significant things do happen to the planet. So there you go. Here's a very nice article describing this. Why is climate sensitivity so unpredictable? Now, the numbers that I showed you would be correct numbers for that 30 gigatons. We would have some time to sort some of this out. But the people in the rest of, and this shows the CO2 emission per person versus the income per person as a function of the year. And I'll play this a couple of times just so you have a chance to look at it. And some of you may have seen me talk about this one before. There's the United States. That was the Great Depression. income went down there. We'll go, and then you can see that as the United States has had more CO2 emissions and more income, they've kind of gone together, and they've gone up and up. But that circle is related to the size of the population. And in these curves here, each one of these dots represents a different country. And what you can see also on here is that there are countries where the income per person is actually comparable, or even maybe in some cases a little bit higher than our incomes, yet the CO2 emissions might be a factor of 4 less, or even significantly below that. And so you can kind of imagine two scenarios. There's a scenario that kind of goes like this for everybody, and there's a scenario that kind of goes like this. And the question is, what will happen to India and China? And what will happen to all the other people in these circles who are poor people who just want to have a good life? And they want to somehow provide for their families. And they want energy to do it. They need energy. They want to be able to cook. They want to be able to go to school. They want to communicate on the internet. They want energy. And so the question is, are they going to go this way, or are they going to go that way? And if they do go this way, then the amount of energy consumption is not 30 gigatons anymore. 30 gigatons is what's happening with just a few countries. If you add up all of these, it's going to be a much, much, much bigger number. So it's a fundamental constraint on the system is that the developing world will and should and must and is going to develop. A fourth constraint, as we try to think about this problem, comes from the scale of the problem. And it's really, really hard to understand this as any person. It's just one of those things, you can see numbers, but they're very, very hard to enter into your head. So 30 gigatons of CO2, that's how much we emit per year globally, approximately. So this number on here shows the top 100 chemicals produced in the world. These are bulk chemicals. This is stuff that gets shipped in giant freight cars, commodity bulk chemicals that we produce. And it shows that the total worldwide of all 100 chemicals produced in the world is half a gigaton. So that's 60 times less than the CO2 emissions. Okay? So it gives you a sense of just how mind-bogglingly huge the amount of CO2 being emitted truly is. It is the single biggest thing that we do, almost, in a sense. And what that means ultimately, I think, is that if we want to find a way of using all of this CO2 in some productive way, the only way is by making a new carbon cycle in which we use the CO2 that's emitted to make a fuel and then use it again as fuel in a virtuous cycle that doesn't have net CO2 flux. Now, I say this is part of the challenge, and it is because anybody who enters this problem will start to think about, oh, I can think of a way to make energy. But the thing is, and we never want to be discouraging to anyone, but the fact is, in the end, you have to think of a way to make energy on that scale. It's absolutely, totally enormous. And many of the things that we think about turn out to be very interesting phenomena, but they're way, way, way down low, and they're not going to have an impact on these total numbers. Now, I also say it's an opportunity. Most of you will know that this is the biggest corporation in America, ExxonMobil. It's the biggest company in the United States. These companies are all bigger than it. You can see Saudi Aramco is, a few times large, several times larger than ExxonMobil. And you can see these, that is just meant to give you a feeling for the fact that the biggest industry in the world is up for grabs. How will it actually be replaced if we do replace it? What will replace it? Nobody quite knows, but who will have it? Who will own it? Who will be the ones that create energy in a way that is CO2 neutral? Nobody knows yet. It's up for grabs. So we can sit on our hands and watch as somebody else goes and grabs it, or we can run out and grab it. Here I just show an example just to give you a feeling for the magnitude of the opportunity. And this is only a tiny example, but this shows worldwide growth of photovoltaics. And what you see here is the growth in the early part of in the 2000s, from 2000 to 2003, whereupon here in 2003, people made a forecast and they said, well, maybe it'll grow at 15% a year. Okay. Maybe it'll grow at 25% a year. These stars show what it actually did. Okay? It went from 600 megawatts to 6 gigawatts in 2009. So then people said, oh, I guess it'll probably be about 10. Turns out it's looking a lot like it's going to be about 15 gigawatts this year. And if you just say, oh, well, imagine that they're selling these things, the modules, at $4 a watt at 15 gigawatts, that's $60 billion industry. So that's not half bad. That's a pretty good industry. And it's still only, a tiny fraction, a few tenths of a percent of where we have to end up, because we need ultimately some numbers of terawatts, 10, 15 terawatts, and we're talking 10 gigawatts, so we're at 1/1000th of where it's going to end up being. Maybe it won't all be solar, but whatever it is, boy, we're talking big stuff here. There's opportunity. Are we going to have these factories be in the United States, or are we going to have them be someplace else? That's a decision that we're going to have to make as we go through and figure out what we want to do. So, does an increase in atmospheric CO2 influence the Earth's temperature? Yes. Is CO2 increasing? And is that increase due to human activity? Yes. So these are said without ambiguity. Can't we simply adapt? Maybe. I don't know. If the temperature goes up 2.5 degrees, and that's actually what ends up happening, there'll be a lot of shifts. Many different things will happen. Maybe some parts of the world will become more favorable than other parts of the world, and life will go on. But there's actually a good chance maybe not. And maybe really significant things will happen, mass starvations, and all kinds of related wars and other problems. And nobody can answer that, to my opinion, definitively. But the risks are very, very substantial. And yet, on the other side, the opportunities of doing something are huge. So those are things that you can contemplate. Just to put it in perspective, again, this just shows carbon cycle as it would have existed without large-scale human activity, which has been relatively stable. In other words, although there's large amounts of CO2 flowing through the system, it happens in a cycle. And I just want to remind you about the importance of cycles. If you were in a high school science class, or grade school, elementary school science class, you probably had to learn the carbon cycle, the nitrogen cycle, there was a water cycle, and there were all these cycles. And I remember distinctly myself being an elementary school student and thinking to myself, this is completely stupid having to learn all these cycles all the time. And why are they all cycles? It's only much later in life that I came to appreciate that there is a fundamental reason for this. Teacher sure didn't know. And it turns out that you can understand it right away. Biological life plays a huge role in the flux of the carbon cycle. It's absolutely enormous, but it is a complete cycle. And that's because as you start to occupy a closed system, and the Earth is essentially, now that we live in, effectively like a closed system. As you occupy a closed system, if you only go half of a cycle, you accumulate your waste. And eventually, it consumes you. So the only way to be stable is to have a cycle that goes around. And that existed for a long time. It has been perturbed due to human activity, which is now 100 times the natural geological flux. And what's happening right now is some of it's going into the atmosphere. Some of it is being taken up by the biosphere, which is using some of the extra CO2. Some of it is going into the oceans with other consequences. But this is an increasingly perturbed system. And the consequences of perturbing it on such a global scale are ones which we cannot even really fully come to terms with. And yet we know that as human activity becomes comparable to natural activity, cycles are the only way to go. This is why we have framed our initiative in terms of carbon cycle 2.0, which would be a cycle that is restored in its balance by the various activities that are shown in here. And the thesis that balance can be restored while allowing for growth in population and well-being. As you know, we spent a great deal of time thinking hard about all the research projects at the laboratory. And if you look carefully at this diagram, you'll see that we have an arc here corresponding to how carbon is used today or could be used in the future: combustion, capture and storage, biofuels, artificial photosynthesis. And then we have a group, our off-ramp here, with efficiency, solar PV, energy storage, and of course the importance of developing world, all commonly treated with a system of energy analysis and climate model. Just a couple of words now before I wrap up on some aspects of CC2. The goal of the initiative is to advance fundamental sciences in all of the important areas that are underlying the energy topics that I just described, and especially also to promote integration of applied, use-inspired, and fundamental research to help create new scalable technologies. And for us as a lab, to be a global innovation hub in this area. We very much want to construct the key analytical and computational tools. I spoke to you last fall about the light source, for example, that we are proposing, very active in the projects to build next-generation computational facilities and others. One of our most important missions is to educate the public, the neighboring community, lab staff, that's what I'm trying to do right now, about energy climate issues and the role the lab is playing in addressing them, to develop more partnerships, and also to greatly improve the energy efficiency of our site, which I'll be talking to you about momentarily. There are many new things planned for the coming year. I went the wrong way there, sorry. There are many new things planned. We're heavily involved in a discussion to establish an institute for energy for the developing world. I've tried to point out to you just how crucial I believe that is. Unfortunately, it falls a little bit between the cracks because, for example, funding inside national governments is always wanting to be directed locally and not globally, and yet we know that our future depends so much upon this. So we're very deeply concerned about this, and we're going to try to organize ourselves better. We're looking very much at the building energy efficiency space for more activity at the laboratory, and especially we are engaged right now in creating a blueprint for an expanded LBL sustainability plan, which would substantially decrease energy use and carbon footprint of the lab. Catalysis is an area where I think you'll be seeing a new initiative within the next year. Biosequestration, I've pointed out a couple of times in the talk that a lot of the CO2 that's being emitted goes into the land, and it goes mainly actually into microbes, somewhat into plants. So we have a group that is proposing a wonderful new project to look at how microbial communities adapt when they are in a higher CO2 environment, and to try to understand the limits. Just how far can we push CO2? How much can we get the land to actually take it up? We will probably be coordinating much more tightly our carbon capture and sequestration efforts via a single center or institute. We are well on our way to establishing a more systematic effort for our Earth system modeling, the computer modeling systems that we've got, for looking also at energy analysis and integrated assessments. So these are new activities that are planned. There's a good chance still that there will be an energy innovation hub announced in batteries and energy storage. And in that case, we intend to compete very strongly for it. We've been in a lot of discussion with Sandia Livermore, who are a lead laboratory in the study of combustion science. Maybe we can help them more. We're very interested in more work in geothermal. There's a lot of thinking going on about what happens to materials like rare earths, which suddenly are critical for energy technologies, but for geopolitical reasons may become scarce. So those are important activities. I want to remind you of the Carbon Cycle 2 seminar series. It's a monthly, or a little bit more than monthly seminar series that has kicked off. These are some of the speakers. You can go and see on the carboncycle2.lbl.gov website the seminar series. I urge you to try to attend these if you possibly can. That's the seminar series. We're in the process of establishing an industrial advisory board for Carbon Cycle 2, and we will certainly be building our ties with industry, because we may be a basic science lab, but we can't really make progress on these problems unless we know what the practical considerations are in the real-world industry. So that's going on. And I'd like to just remind you that I consider this Carbon Cycle 2 initiative to be by far the most important thing this laboratory can work on from a national and global perspective. And so it's the job of all of us to be thinking all the time, is our energy and environment research really being successful enough? Can we do more? Can we be better at it? Can you reach out to others around the lab and get help from them to speed it up? What are the key science and technology breakthroughs? Where are they going to be occurring? And we better try and be right at the focal point, at the fulcrum of those. Are we focusing on the right problems? And can we do better? Thank you for your attention. So I understand there's going to be a couple of microphones circulating, so I can take some questions from you. There's one right here and one there, so I'm happy to take any questions if you have them.
Check. I just wanted to ask a quick question. To what extent do you think human population growth compounds this problem? And if it is the gorilla in the closet, why do we not discuss that more?
Well, sure, population growth is related to it. And as you know, related to it is the desire of people who don't have a lot of means to develop. And typically, as economies develop, the population moderates more. My honest belief is that it's actually quite straightforward for us to imagine a future in which this problem of the carbon cycle is eliminated without having to directly get into issues of population growth, because the amount of energy coming to us from a variety of renewable sources is more than enough to meet our needs. So my sense is, obviously, the issue of population is an important one, and it's one which is going to regulate over time as development occurs more broadly. That's my opinion.
The
Yes.
amplitude of the CO2 variation due to the seasonal change in the last 40 years does not appear to have changed, at least when I was looking at your plot there.
Yeah.
And yet we have deforestation, net deforestation, or does it say that what is the reason why that amplitude isn't changing?
Yeah, I haven't studied that issue specifically, but I would say that we also have, when there's more CO2, more living things are growing. So, for example, there are a lot more microbes in the dirt in some places than there were previously, because and also some plants are growing more. So, I don't know actually in the end the net answer to that, Phil, but I will look it up. I haven't thought about looking at the amplitude. It is, yeah. This issue of how the biosphere responds to an overall change in the amount of CO2 is a very interesting one. And also, as you say, that amplitude, the deforestation. So I haven't looked at it enough, and I will look more.
One back here.
Paul, you gave a wonderful talk, but I have some questions.
Sure.
China and India. China and India will have to develop their technology with carbon, because carbon is cheap.
Yes.
And I understand they build a power plant of 1 gigawatt every week,
Yep.
carbon-fired. So the big problem I see is in the CO2 production. What can we do to keep that under control?
Yeah.
Are there ways to sequester CO2?
Yeah.
Or can we convince them not to use it? But how would you do that?
Yeah.
Because there are huge numbers of people there, very poor, and they want to have a better life.
Yeah. Well, first of all, with respect to capture and sequestration, let me say, and I took some of these things out. I have another presentation I give that goes much more into possible technical solutions than what I did today. But if you look at scenarios for ways to bring the carbon down over the next 50 years, and we've learned so much from the Princeton group, from Bob Sokolow and colleagues who have thought a lot about this concept of wedges. We'll use all the different techniques at our disposal. There doesn't seem to be any scenario that brings CO2 down that does not involve a substantial amount of capture and sequestration, because partly for the reasons you're mentioning, combustion is the most easily accessible form of energy, and also it's the most widespread. And it turns out it takes decades. Even if you decided today, I'm going to completely change the energy system, it just is such a large-scale infrastructure that it takes many decades to do it. So that means combustion will be with us for some time. That's why improving the efficiency of combustion is still important and still can be done. But on the other hand, capture and sequestration is a very key and important thing for us to be looking at, because we're almost certainly going to have to resort to it. Presently, the cost of capture amounts to, if you like, think of it as about 8 cents a kilowatt hour to capture CO2, approximately. Or from a thermodynamic point of view, if you're running a gas turbine engine and you say, how much of the energy of that that I'm burning has to be used to capture the CO2, it's about between a quarter and a third. The thermodynamic limit is probably 3 to 5%. So we're off by a factor of 10 from what we could achieve thermodynamically in capture, and presumably that means that cost could come way down to a couple of cents a kilowatt hour. Let's do the science to get that done. So there's a group here working in an Energy Frontier Research Center, Jeff Long and his colleagues, Bernd Schmidt, with Omar Yagi from UCLA and others. Let's try to find materials that will help us bring the cost way down. And then, of course, there's the issue of sequestration. And the sequestration might involve burying the CO2 underground in geological reservoirs. And we have a great team here that's looking at that issue, too. We have very close ties with China, for example, in the study of CCS, carbon capture and sequestration. Let's work together to try to find the solution for that. I will note that China, for all of its sometimes vilification, in the last, our China Energy Group has found, for example, that in the last 20 years, when their GDP has quadrupled, their energy use has only doubled. So their efficiency has gone up by a factor of 2, admittedly off a low base. And when I look at areas like renewables and see the incredible efforts that they're making to bring the costs down for producing solar, for example, the investments that are being made there, and the tenacity with which they're pursuing that issue, I think we would be remiss if we said that somehow they're not trying to hold up their end of the bargain. China's really working very hard on these issues. We need to sort of keep pace.
Is the direct input of heat due to combustion of hydrocarbons negligible relative to the indirect effect of greenhouse gas?
Yes. Yes, it is.
Yes. In discussions with colleagues and friends, very frequently I'm surprised at the extent of skepticism that any of this global warming or carbon efficiency or energy, that there's even a problem there. And if we ever considered like forming a website with specific answers to a lot of these questions, where we as scientists and colleagues can refer people who have these questions.
Yeah. Sure. So we're trying this year to beef up the Carbon Cycle 2 website, which should have a lot of this kind of information on it. This presentation is going to go up there, and a number of other sort of ways of trying to get that information out there. Unfortunately, I think, as you know, this issue has become wrapped up in a variety of cultural and political dimensions. But the science remains the science and is what it is. And so I think it's important for us, at least as an institution which has truly global reach in the science world, to state very clearly what we know to be the correct science and put it out there as best we can so that it's a part of that, so that that piece of it at least is stated as clearly as we could possibly get it to be. I just wanted to say briefly, because I was asked the question, is the direct heat from the burning negligible or not? And I just gave it the quick answer, yes. But I just let me give you a feeling for that. Think about the total. If you tried to calculate the total, to give you a feeling for how much energy comes from the sun, it's about 7,000 times more than the total energy that we use. So that gives you just a feeling for it, how much larger it dwarfs it. And that's why, even though but what happens is when the CO2 goes into the atmosphere, that very large excess of photons that are coming down and heating the planet, the rate at which it's cooled is altered by even just a very small amount of the CO2. It's the way a little insulator layer can have an enormous impact on the temperature of something. And so that's qualitatively a way of thinking about that.
Can
Yes.
I ask? If you compare the United States with France, for example, then France emits 1/3 of the CO2
Absolutely.
per person, 6 tons, and States 20 tons. So
That's
why
right.
did you ignore completely nuclear energy?
Yeah. No, indeed. It's very impressive what has happened in France with the nuclear, and I'm very much a supporter of seeing us have a revived nuclear industry in the United States. We have been stuck in a mode where it's not happening very well, and part of that is, again, because even now when all the regulatory environment is saying that they're favorable to it, the financial environment isn't turning out to be favorable. We have a system where you have to somehow capitalize these, multi-billion-dollar kind of activities, and the sense of private capital is that they consider it too risky, which means, to my mind, that this is something which could only be resolved by a true government policy, a true energy policy, which would say, okay, we're going to promote nuclear, and we're going to make state investments, which is, of course, as you know, what has happened in France. On the nuclear side, there is a lot of important research to be done as well, because we don't burn down the nuclear fuel well enough, and because of some of the proliferation issues that can arise when the burnout isn't done quite correctly. And I would very much like to see us partner with some of the other laboratories which have really very deep and extensive programs. For example, I mentioned in the case of combustion, we'll probably partner quite a bit with Sandia. In that same sense, Argonne and maybe Oak Ridge and the other laboratories have a deeper portfolio of nuclear programs. We have some pieces that we could contribute to that in terms of new fuel cycles and things of that type. And I think one of the issues that has discouraged me a little bit has been the fact that we don't have much of a policy, and it's been hard to establish a strategy for the lab when there's no kind of framework to put it around. So we're struggling with that.
Hi, I'm wondering, what if there's not a technological solution to this problem?
No technical?
What if it's primarily a cultural problem? And what if the problem is an economy premised on throughput and infinite growth, and that's just not reconcilable with the science? What role does the lab and play in that scenario?
Yeah. It's amazing how many problems which are at one level of technology strictly social and political ones, at another level of technology just go away. Because just there's a development there which permits you to move beyond it. So my opinion on that is that there are multiple dimensions to this problem. Clearly there's a social and political and economic one, and on the other hand there's also technical and scientific components to it which are very large. And so, the laboratory will play in certain parts of that. I will say my own view, and not everyone necessarily needs to share it, but my own view from thinking through it, for example, this number of sort of a factor of 7,000 roughly between where our energy needs are and what's potentially available to us just from that one source of solar, not counting many others that are available to us, is that essentially we do live in an abundance of energy. So the population issues are going to be there that we need to think about. But the possibility for us to have growth and energy without the CO2 problem are just all over the place, and we just need to seize them. And so my own personal vision on that is that, as the population grows, the carbon problem is the first one because we're so sensitive to it. But we will encounter a series of other related types of issues that come from the fact that people are now such a large fraction of just the Earth's overall equilibrium. So that's another reason why I think it's very important for the lab to get engaged in these problems at the level of the entire planet, because there are going to be a series of issues like this as we go along. But I remain very optimistic that they're quite solvable. The planet's a very good home for us. We just need to take very good care of it. Question back here.
Just looking over the problem, one of the things I'm always struck by is it seems like a lot of the things that we can do to help it sort of scale linearly. You add more panels, you get a little bit more renewable energy.
Yes.
A lot of the sort of downside things that can happen, like loss of coral reefs through bleaching and things like that, have essentially catastrophic onsets. Like they're
Yes.
And I was just curious about when I talk about friends of mine that are not scientists, it's often difficult to sort of talk about risk management in such an environment. And I was just curious about your thoughts on maybe how we as scientists could better characterize that distinction.
Yeah. Well, first of all, what you said is pretty much correct. You know, there are certain, there can be, the global ecology has sensitive points to it that can really be transcended, and the consequences are then difficult to reverse. So there's no doubt that that's the case. And at the same time, we're trying very hard to develop a different way of thinking altogether. We're still, you know, because of, you know, essentially all of civilization history, we've had the possibility of existing in an environment where we could use energy and the environmental consequences didn't matter. And in fact, we could use almost anything and the environmental consequences really weren't so significant. And it's only as the population, as technology has improved, the population has grown, that we've entered into this constrained environment where we can't just do anything anymore. We actually have to think about the system and how all the intercouplings arise. And it's a major challenge to science. I mentioned to you, for example, we can't figure out all those feedbacks very easily. It's a very complicated system. So, you know, it's clear that this is going to be a challenge for science for many, many decades to figure this out. My sense, though, in terms of talking to your friends is I think, you know, it is an interesting philosophical issue because some people, I think, approach this issue from an understanding that nature is fragile, and others approach it from a different point of view, that it's infinitely robust. And so this is a dialogue. And I think you'll see ups and downs in that dialogue. So sometimes you'll see that the political system appears to be sort of running away from what the science is saying. But the science, I think, is so strong in this case. We'll pull them back, and we'll have a better discussion, you know, as we get, you know, the facts out there more.
Yeah, as we look at kind of the terminology that is up here and kind of the ultimate outcomes that we're trying to get to, would we say that most of this is related to just removing it or making it more efficient? Or are there other outcomes that are not addressed or that I'm seeing just in terms of synthesizing kind of an ultimate outcome of the cycle?
Yeah. The answer is yes. The answer is, you know, so this diagram only shows part of what's possible. For example, the question around nuclear a moment ago, it's not even on here. But fundamentally, I believe there's two parts to it. One is to devise a cycle that uses carbon, but in a cycle. And the other one is to just get off the carbon altogether and just not be using it. And the answer is we should do both. So, you know, efficiency will be a big part of it. Nuclear can be a very big part eventually. Solar and batteries, these things take us off that curve. But these ones leave us on the use of carbon. Just use it better and better and in a more stable way.
Just as a quick follow-up, outside of then those two outcomes of either getting off of it completely or devising a way to use it more efficiently, is there a third outcome or any others that you see?
It doesn't occur to me offhand, I'm sorry. But if you have an idea in mind, I'd love to hear it, you know? Yeah. Okay, I have people pointing their fingers to me that it's time for me to excuse us, so we're done. Thank you.